Hey AP Calculus, I've got a new video for you. This is, I guess we'll consider it 4.7. I'm only going to go over one example, and it's number 35 from the Anton problem set. So my apologies for the blurriness of this. I think we'll all get over it. All right, so it says a point P is moving along the line whose equation is y equals 2x. So here's what y equals 2x looks like. It starts at 0, 0. It's got a slope of up 2, right 1, up 2, right 1, and it pretty much looks like this going in the upward direction, and it looks like this going in the downward direction. Okay? How fast is the distance between this point that's moving along the curve and the point 3, 0 changing at the instant when P is at 3, 6? Okay, so this is really, really tricky situation, but visualizing it, it's kind of like saying we've got a red point that doesn't move. 3, 0 does not move. But the point along the line is continuously moving. All right? So it's sort of like the distance between the point 3, 0 and this point at this particular moment is going to be that distance. But then it turns into this distance, then it turns into this distance, then it turns into this distance and this distance. So as you can see, any point moving along this purple line is going to change its distance when it keeps moving forward. Does that make sense? Yes, Mr. Owsley, it makes sense. So what can we do? Well, first of all, we have to determine what's our primary equation. What's the thing that we're optimizing? What's the thing that we're taking the derivative of? Well, this imaginary red dashed line represents the distance between 2 points. So it stands to reason that the distance formula is going to be our primary equation. So our primary equation is going to be the distance formula. Now, hopefully you guys have that committed to memory. It's the square root of our x coordinate subtracted squared plus our y coordinate subtracted squared. It's basically another version of the distributive property, not the distributive property. It's another version of the Pythagorean theorem. If I squared both sides and get rid of this root, a squared plus b squared equals c squared is really what we have going on with the distance formula. I don't know, maybe it's helpful for you guys to remember. Whatever, right? So then, we've got d as the formula we are taking the derivative of. So the first thing I'm going to do is I'm going to get rid of this square root and rewrite it as a fractional exponent, because it seems like fractional exponents are a heck of a lot easier to work with than like radicals, right, with derivatives. We also know that 3, 0 is a point that never changes. So the distance between 2 points, we can call this point that's constantly moving along the curve or moving along this line as x comma y. So let's do this. Let's say that our x1 and our y1 is this point that keeps changing. So I'm gonna replace x1 and y1 with just x and y. Okay? Now, the other corresponding point that completes the distance formula is 3, 0. So we're saying x sub 2 equals 3 and y sub 2 equals 0. So I'm going to replace x sub 2 with 3, and I'm going to replace y sub 2 with 0. So what we have so far is d equals x minus 3 squared plus y minus 0 squared, which is the same as y squared. All of it inside of this, this root that we've turned into a half power. Now, I didn't even read the last statement here. It's changing at the instant when the point is at 3, 6, if x is decreasing at a rate of 2 units per second. So we know what dx dt is, all right? if x, I'm sorry, it's super blurry. If x is decreasing at a rate of 2 units per second at that instant, we know that we're going to be plugging in x equals 3, y equals 6, and dx dt, once we take the derivative, equals negative 2. So if we could get rid of this y because we don't have dy dt, that would be awesome. So the question is there a secondary equation of which we could plug into this equation right here? Right there. Okay. So y equals 2x is going to be our secondary equation that allows us to rewrite our distance formula totally in terms of x. So that's what we're going to do. We're going to, by the way, we are not going to replace this until we take the derivative. Just keep that in mind. This is after taking the derivative with respect to t. Anyway, so we're going to replace y squared with 2x squared, with 2x. All right, now, it's kind of complicated in there. I would advise doing algebra first. So let's go off to the side where we've got a little more room to work with. So I'm going to expand this polynomial right here. X minus 3 squared is going to come out to be x squared minus 6x plus 9. And then 2x times itself is going to be 4x squared. The whole thing is still to the half power. Then I can combine like terms here. And we finally can take the derivative of this function because we're looking for the rate at which the distance is changing between the 2 points, which is d dt. Yeah. So the change of the distance with respect to time is bring the half down. We got to do chain rule. Rewrite the inside. Don't take the derivative of it just yet. Take 1 away from the power. Multiply by the derivative of the inside. I hope you guys can see that. You can. Okay. 10x minus 6. Awesome. Oh, shoot. When we take the derivative of the inside, we took the derivative of x terms, which creates a dx dt inside of there. So we still have a dx dt. Okay, so I'm going to simplify this by distributing the half to both of these terms right here. Half of 10x is 5x. Half of negative 6 is minus 3. So that'll be the top part of my fraction. I can move this to the denominator because it's a negative exponent. And you know what? I'm just going to change it back to a root. Okay? The half power means a root. So it's root 5x squared minus 6x plus 9 on the bottom times dx dt. And then at this point, this is where we can plug in our initial conditions. Remember, x equals 3. We don't have a y, so we don't have to worry about the 6, but the dx dt gets negative 2. So plug in 3 for x, negative 2 for dx dt. And I'm going to put negative 2 over 1 just to remind ourselves that, hey, we're multiplying the top of that fraction times negative 2. Sorry. The multiplication dots don't show up so well on the YouTube videos. So this is going to be 15 minus 3, which is 12. 12 times negative 2 is negative 24. That's going to be our numerator. In the denominator, it's going to be 5 times 9, which is going to be 45. 45 minus 18 is going to be 27. 27 plus 9 is 36. We got negative 24 over 36. That's going to reduce down to negative 2/3. All right, so the distance between the point 3, 0 and any point traveling on the curve at the given instant that we're at the point 3, 6 is going to be negative 2/3 units per second, or decreasing 2 units every 3 seconds. Decreasing 2 units every 3 seconds. All right. Can you guys see that final response down there? You can. All right. Wow. So that's the last application type problem I'm going to show you guys. We're going to get a review set out to you, and then we will take that test on Friday. Thanks for watching.